So I'm now continuing on part 3 of this introduction to a dynamical system. So we have seen now that there are 3 types of critical points, which are attractor, repulsor, or saddle point. So just one more information about these points. For specifically the saddle point, it's possible to get more about the local structure. So remember, there is one direction where you have everything is attracted, and one direction where everything goes away. And of course, the trajectory is here, forming some type of hyperbolic structure. And so this picture in dimension 2 can be generalized in dimension n, and you can define what is called here. This line is called the unstable. There is unstable manifold, and this is called the stable one. So basically, you can look at this by considering all the space in the tangent space. You can consider the subspace generated by the eigenvalue, let's say U1, UK, which are associated with real parts, such that the real part is positive. So you have this first space generated by this, and you have this. So this is going to generate the unstable manifold, while the stable manifold is generated by the complementary, which is UK plus 1 plus UN, such that the real part here, so K plus 1, such that the real part is negative. Real part of lambda n negative. And so you can show that these two spaces are our interest, and it's very hard to study how they prolong outside a neighborhood here of this critical point, how they behave far away. Right, so I think we are basically done for this introduction. Maybe I should say something about what happened when the real part is 0, and give an example, which is really the classical example. So what happened when the real part is 0? So in dimension 2, I think the most classical example is this one: x dot equal minus y, and y dot equals x. So here 0 is a critical point, but you see there is no convergence of trajectory, because as you can see from this, if you multiply this by x and this by y, you get x xy plus y yx equals exactly 0. So the circles are the integral trajectories equal constant, which means what is doing the dynamical system, you know, our trajectory, once you are at a given distance, you are just making rotation. Right, so those are the trajectories of the systems. This is x of t equals, let's say, cosine t, and y of t. So there is a constant here, c of t. So you are really making a rotation. So this is very different from the classes that we studied previously. Now, an interesting notion is the notion of basin of attraction. So what is the basin of attraction for an attractor? This is the maximal, the biggest set, such that if you start at a position x0, then you converge, let's say, basin of attraction of the point P0. So if you start at this point, the trajectory x of t converges to 0 as t goes to infinity. So the basin of attraction B of P0, this is the ensemble of x0 in your space, such that, and this is the maximal set, the maximal set of x0, such that when you start at x0, you converge to 0 as t goes to infinity, x0 equal this. And so this is usually very interesting to understand what is B, and in particular what is the boundary of B. So you have P0, and you are really interested in some cases at what happened at the boundary. And of course the boundary has a very peculiar structure that has been studied, but we're not going to enter into much detail here. Alright, so now the next, I would say the next simplest limit cycle is the recurrent set is the limit cycle. So what is the limit cycle? The limit cycle for a dynamical system x dot equals bx. This is a trajectory. It is a closed trajectory. So this is an example of a limit cycle. So this is a solution x tilde. It is a periodic solution of period of minimal period capital T. So such that x1 of t plus capital T equals x of t for all t. And so now you can ask, what's the stability of a limit cycle? So and of course x of t here is a solution of 1. So how do we study the stability of a limit cycle? So what can happen actually? Either the limit cycle, so we are in dimension 2. So if we are in dimension 2, either trajectories goes around, and so you have a stable limit cycle, or the opposite is that the trajectory goes away, and this is unstable. And basically in dimension 2, that's it of what can happen. So what's the manner to study this type of behavior? Well, if we have a dynamical system which is given by an analytical expression, then a part of dynamical system theory is to explain how this can be put in a very specific form, which is called a normal form, where we can write basically if you are in polar coordinates, where x can be represented by the distance r and the angle theta, then we can write an expression for the dynamical system in this coordinate r dot and theta dot. And when we can succeed to make it in the form theta dots equal constant, let's say equals to 1, this can be more complicated depending if the dynamical system has critical point on it, but let's assume that the vector field on the cycle never vanishes. So B along the cycles is never 0. Then we can always have something of this type, theta dots equals 1, And then r dots, in the general case, is a function of r and theta. And if we can succeed to have this as just a function of, let's say, this can be even put as a function, let's say a function just of theta multiplied by r, then it's enough to study this A of theta if we want to have the stability of the system. And this is true actually also in dimension, in higher dimension. Instead of r, we can have transversally. So if we're in dimension n, you can look at what happened transversally, have a system of coordinate x1, xn minus 1, and generalize this, where we can have an ensemble of equation for x1, xn minus 1, which I will call x tilde. So this can be put in the form a theta of x, and theta dot, so this is dot, equals, let's say, 1, a constant. So again, to study the stability, it's enough to study the stability of this part, and we are back to what we have seen for a single point, because now it's an attractor or repulsor or a saddle point in dimension n minus 1. Alright, so this is, I'm not going to enter much into detail for this, but this is a way to study the stability of limit cycles. Again, this is a bit abstract, but this is a general procedure. And of course, you can have more complicated recurrent sets. So maybe we should, just to give another example before we go to some definition. If you have a torus, now the dimension of this ensemble is 2. And what happens is that you can have trajectory that comes and rotates along the torus. So this, in that case, you have a stable torus. The field on the torus is can be actually completely classified depending on if you can map. You can always map this into 0, 1 and look at what is called the trajectory on this map on 0, 1, and see and look at the angle here that the trajectory is doing. And depending on the angle alpha, if it's rational or not, you can, and this is, again, very classical, you can either have dense trajectory or closed trajectory. So this is closed, and those are dense trajectories. So in general, because studying the future of a dynamical system is quite complicated, to study what happens when t goes to infinity, a trajectory can visit some points, can visit some cycles, can go into some regions, and can go back and forth. Again, this is, suppose this is in dimension bigger than 3. So it can go back in here. I do it like this because to say that I don't want to give the impression that we're crossing trajectories, just going below in dimension 3. So the concept that came was that we should not look at what happened continuously with time, but at a discrete point. And so there are two interesting sets, which is called the omega alpha recurrent set, which is basically all the points x such that we can find an infinite number of points, a sequencer that goes to infinity, such that the distance, any distances of in dimension n is okay, between the point x and your dynamical system at this Tn, this goes to 0, which means that you can find an infinite number of points that will be as close as you want from a point x. And so this is called the omega alpha recurrent set, and you can have also the same for, so this is called omega beta, which is the same, except that we want to have the trajectory Tn that goes to minus infinity, for which the distance to x is going to converge to 0. So that are the two interesting sets that defines the where we can find the trajectory of a dynamical system. So now we are going to stop here and then discuss some examples of bifurcations in the next session.